you would expect that the matter would have been ejected uniformly all around. And so you would expect that the universe would be pretty uniform everywhere you look. But now that we look at the universe, it's not. That's very chunky. You, even though in the night sky, we see the stars. If you zoom back out of our solar system and look at the stars, you see that a lot of stars are kind of clumped together in neighborhoods. And then when you zoom further back, you'll see all those stars are actually living in a galaxy together. And then there are wide open spaces, and then there is another galaxy. You further zoom back, you'll see that the neighborhoods of galaxies together. So it's very, very clumpy and chunky. So what has happened? How has the universe evolved from the Big Bang to what it is today? Coming back to the next slide, more interesting questions. Where did we come from? Again, think of the Big Bang. Big Bang, the very first few seconds, all we had was a very elementary subatomic particles, building blocks of atoms. And then soon after that, those particles combined together to make a proton and a neutron, an electron, and you got ionized hydrogen basically, which is the simplest element in the periodic table because it only has one proton. And then of course the electron got captured and you got neutral hydrogen, but that's the simplest element that could possibly exist at that time. But you look at it today, what are we made of? You know, we are made of carbon, we have iron, we need oxygen. So if you look at those atoms, they are very, very heavy atoms. Each of them have multiple protons in them. And so how did the hydrogen atoms gain protons to make the next element? And we know that the only way you can put another proton into an atom is by fusing another proton into an atom, which takes a hell of a lot of energy or some kind of force that can push those protons together. So from one proton to the multiple proton elements that we have today, how did they come about? Because if they hadn't, we wouldn't be here today. So that's an interesting question. Next slide. I think that's the most interesting question. That is, I'm sure everybody has thought about it at one time or the other. Are we alone in this universe, or are there other beings somewhere else in the universe? Whether or not they're intelligent or they're just microbial, are they there, or are we the only ones? The answer to that question, either way, is a very profound answer in my mind. Either we are the only one in this huge universe, and so we are very, very special, or that we're not that special, and there are other life forms in the universe, perhaps even more intelligent than us. And so how do we look for them? How do we find them if they are there? The easiest way would be that if one of them shows up in our neighborhood, park their flying saucer in our backyard and say, hello, I'm such and such, come from planet blah blah. That's the only way we will know for sure that they are here. Things are very far away in the universe from us. Our closest, we have looked at our own solar system that we know for sure there is no sign of life, at least an intelligent life, in any of our planets. The next star from us is 4 light years away. And so, by the technology that we have, even if there was life that we would go to look for it, the technology of traveling in space, it will take probably thousands of years for anyone else to go there and see if there's life form here. So all we have is, again, relying back to remote sensing. Can we detect light remotely by sitting on Earth? What do we need to observe in the universe to detect if there is any life? So we'll talk about that in a little bit. Next slide. So the last 10 or 15 years or so, the new mystery has come out, which we're calling dark energy. Of course, dark matter has been discovered a very long time ago. So there's evidence of there's a matter that exists in the universe without which we could not explain the behavior of the universe, but we know it exists, but we have no clue what it is. And we're still searching for some clues, and so once you don't know anything, we just put a word dark in front of it. So you say, okay, there's some dark matter. And then since Hubble was launched, we discovered, Hubble was launched to answer one of the questions you were supposed to answer is, what's the fate of the universe? After the Big Bang, there's an explosion. Like if you throw a ball up in the air, because of the gravity, the ball will come back. So the Big Bang explosion, depending on what the mass of the system is there enough gravity in the system that it will slow it down and pull it back again to a big crunch and have another Big Bang? And if that's the case, is ours the first Big Bang or is it the 20th Big Bang? We don't know. If there's not enough matter, if there's not enough gravity, the universe will continue to expand, it'll cool down and eventually cool off and die. So to answer that question, we needed to figure out what the Hubble constant or the mass of the total mass or the gravity in the universe is. But instead of answering that question, Hubble discovered that even though the universe is expanding for several billion years, but last 6 or so billion years ago, it started to accelerate. It started to go faster. It started to expand faster than it was before. So I don't know if all of you have studied physics or not, but Newton's first law of motion says that if a thing is moving in a uniform velocity, it only can do that if no force is acting on it. But if it's accelerating, it's going faster, then there has to be a force that's causing that acceleration. So if the universe has started to accelerate, there must be a force or an energy that has somehow appeared that we didn't know about. It's causing the universe to expand faster. So we, again, don't know what that is. So we call that dark energy. So these are some of the major questions that we're trying to answer. And that's why we're building bigger and bigger machines, different kinds of machines to study the universe from a different perspective. Next slide. So like I said, humans been observing the universe for centuries, but until very recently, we've been relying on what we observe with our own eyes. And we're recognizing now that our eyes are of very limited, optimized for a very limited band of electromagnetic wavelengths that exist in the universe. The top curve shows the whole range of the electromagnetic radiation that's coming out from different objects in the universe, anywhere from very long radio waves to microwaves to all the way to gamma rays. We are only seeing a small band in the visible light with human eyes. So you can say that we have blinders on, we can only see what we are built to see, and therefore we have no knowledge of what other wavelengths are carrying in terms of the information. So if you could look at the universe with those eyes, we can probably put more things together and probably get a better understanding of what the universe looks like. The problem, or actually the good thing about our atmosphere, is that it doesn't allow some of those very harmful radiations to come through and protect us, which is good. But it also means that we cannot observe those wavelengths from the ground because they're not accessible to us. Also, if you were to look deeper and deeper into space, you can imagine the farther things are, more dimmer they will be. You know, if you take a bulb and start moving farther and farther, it will get dimmer and dimmer and dimmer. And if you take a picture of that bulb that's very, very far away, if you know anything about photography a little bit, what you have to do is take the biggest aperture, open up the aperture of your camera to as large as you can, keep the camera very stable so it doesn't move, so that it can collect as many photons over a long period of time, and it will eventually give you a sharp image. Another problem with our atmosphere is it doesn't have a very constant density. So because of the heat, temperature variations across the height of the atmosphere, the density is very varying. So as the light from a very, very distant object comes through, the image moves. This is what we call, you know, the kids know the twinkle, twinkle, little star, right? You've heard that? That sounds great for a nursery rhyme, but it's a pain in the neck for astronomers because they cannot take pictures of very, very deep objects staying on the ground. Of course, now the technology has evolved where we can actually adjust the optics to account for the twinkling of the stars. But because of that atmosphere, that's another reason why it's important to have telescopes above our atmosphere. So this picture kind of shows the various telescopes that we have built that are optimized for different wavelengths. So some of these Planck, Herschel, and all are very large, long wavelength microwaves, infrared, Hubble, of course, in the visible, and of course X-rays, gamma rays, and so forth. And James Webb is now being built with the optimization to be able to see infrared light. I will talk about that, why that is. Next slide. So this is what we know so far about the history of our universe. So we had a Big Bang, and a very few microseconds, and even smaller than microseconds later, the universe really expanded very fast, faster than the speed of light, and it cooled down. So that's when the hydrogen atoms started to form. The light that was there from the initial Big Bang disappeared because there was nothing to light it anymore. There were just atoms. They didn't produce any light. And so the universe went into what you call a dark age. So there was no light for 400 million years. This is how long it took for those hydrogen atoms to start colliding together to make a bigger mass. And as you know, rolling ball gains mass. If you roll a ball in snow, it gets bigger and bigger. So that hydrogen atom started to get bigger and bigger and started to collect more and more mass. And over 400 million years later, it became so huge that the gravity force of that mass that was exerted into the center of that mass pushed the two protons of hydrogens together and created the fusion reaction and created the energy equal delta E equals mc square. So the mass combined, it was slightly less mass in the end, but the rest was energy. So that's how the fusion works. You put enough force into the atoms to put more protons in it, and so the star started to burn. That's where the light started coming out of the universe, and of course that energy started to balance out the gravitational force. The gravity would tend to pull you in, the energy will try to push you out, and the star became into equilibrium and started to shine. And so 400 years later, the first light appeared in the universe. We'll talk more about what happens to that star. But what happened here is the hydrogen became fused and started to make the next element in the periodic table. So we had the first light coming out 400 billion years after, and then from there we can see how the universe started getting clumpier and clumpier and started to expand, and then a few billion years ago it started to accelerate. Next slide. So you may say, how do we know about this? How do we know what happened 13 billion years ago? How can we look in the past? So that has to do with speed of light and the distances that we are dealing with. So let's look at the moon. Moon is, in light years is a measure of distance, right? So it's how far light can travel in that year of time. So moon is 1.3 seconds away from Earth. So when you're looking at the moon, you're looking at it 1.3 seconds ago. Next slide. The sun is 8 minutes away. So when you're looking at the sun now, it was really not there. Now it was there 8 minutes ago. Same as Neptune, 4 hours. Neptune is 4 hours away. Like I said, the closest next star to us is 4 light years away. Let's say that you had a relative there, and he takes a picture of himself and emails it to you, to Earth. And of course, let's say that the email comes at the speed of light, so it takes 4 years for that picture to come to you. So when you're looking at that picture, your relative is not that person anymore, it's 4 years older. So you extrapolate that. If you're looking at things farther and farther away, you're looking at the light or the picture of that image as it left that long ago. So this is what Hubble has done. You can take a snapshot of galaxies nearby. You can tell how far those galaxies are. So you can see how far back in time you're looking at and what they look like. So as you go farther and farther and farther, you can see this light has taken maybe 11 billion years to reach us. So what we're looking at it now is what it used to be 11 billion years ago. So now we know the history of the universe. It looked like 11 billion years ago. And so that's how you figure out the history of the universe. The other thing you notice is that as you go deeper and deeper, and that means farther and farther away, the colors of the galaxy have started to turn into red. And we'll talk about that in a minute. And that's where the limitations of Hubble start to show up. Next slide. And that has to do with Doppler effect. Again, some of you who are not familiar with physics, you probably are ever been into a train station or standing on a road and a car is coming by, it's beeping his horn, and it's coming towards you. The horn sounds high pitch, and that goes by you, it goes high pitch. That's because as the sound is coming to you and the car is coming to you, it's compressing its frequency of that sound that's coming to you, and so the sound is coming faster and faster, and so it looks like it's at a higher frequency as it's approaching you. And as it goes by you, each sound that's emitted is coming later and later, and so the frequency is getting longer and longer, and so it sounds like it's a high pitch. What we know about our universe is that the universe is expanding, therefore everything is moving away from everything else. And farther the galaxies are, the faster they're moving away from us. So the Doppler shift is taking effect even in light. So as the light may be invisible from this distant galaxy, but as it's moving away, by the time we detect that light, it's turned into infrared. And Hubble, like I said, is optimized for visible light. It has a very tiny sensor in near infrared, but mostly it's visible and very little in the UV. So at some point, we believe that Hubble is no longer able to see beyond certain distance, because even though the galaxies may be there, we just cannot detect the light. Next slide. So this is a very famous Hubble deep field image. We pointed Hubble to a very ordinary dark portion of the very tiny sky, maybe the size of looking through a straw. And we said, okay, if there are things that are so fine that we cannot really see it, so let's do that photography trick. Open up the aperture, let it stare at the spot for 11 days and see what we get. And after 11 days, it collected this image. And in this image, each and every point of light is a galaxy by itself. It's a galaxy made out of trillions and trillions of stars. And that's just in this little tiny portion of the sky. So just extrapolate that all around 360 degrees to give you an idea of how vast the universe is. But you're also noticing, again, the colors are changing. The closer galaxies are bluer, the distant galaxies are red. Next slide. And so we believe that even though we see dark areas, we can't be sure that there is nothing there. We believe that there are older galaxies that are emitting light, but they're in infrared, so Hubble cannot see it. Next slide. So we believe the light is there, it's coming to us, but we haven't yet seen it, even with Hubble. So that's where the need for an infrared telescope comes to be. Next slide. The other thing that Hubble is limited because it doesn't have infrared is that, like I said, the stars was born and it started to fuse. The very first generation stars were fusing hydrogen, and at one point, after maybe a few billion years, depending on how big the star is, that fuel eventually exhausted, right? It used up all the hydrogen that it had, And so if the size of the star was only big enough to create enough gravity to fuse just a single proton together, it didn't have enough power to fuse the next generation, the two protons and two protons into 4 protons. The energy stops. It cannot hold the gravity force anymore. And so the gravity pushes all the matter that it has created towards its core. And since the core is now very hard, it hits the core, bounces back out, and it gets ejected all over into space. And the same process starts again. That dust that has a higher next generation elements in it starts to gather mass, starts getting bigger and bigger. Now it has to get much bigger to start fusing the next element. And so in the throes and the death throes of a star, new stars are born, but they are born in the middle of the dust. And so dust doesn't let the light come through as easily. So Hubble cannot really study the births of stars that are happening inside the nebulas or the dust clouds of other stars very well. So that's another reason why we need, can you go back? Infrared light. So in this picture, we have the same picture, one taken with visible light, one with infrared, and you can see through this opaque object the hand of the person, because the infrared light is produced because of the temperature, and so the hand is probably warmer than the trash bag it has. So infrared machine could probably penetrate through the dust clouds and observe how the new stars are being born. We'll talk a little bit more about that. Next slide. So this again, like I said, using Hubble's limited near-infrared capability. This is a picture of dust clouds. We call it fondly the pillars of creation, that a star has exploded and it has ejected its matter. But you can see some glow either coming from these clouds or around the clouds. So we believe there may be something either in these clouds or behind the clouds that are causing this light. But when you use the near-infrared light, next slide, you can really see through that all of these hundreds of new stars are being born inside the dust cloud. And so that's another reason why the scientists decided that we do need another telescope that is optimized in infrared light. Next slide. So that's how the James Webb requirements came to be. The scientists said we need something like Hubble and optimized in infrared light, but just the size of Hubble is not enough. We need much bigger mirror. So we negotiated them to a 6.5 meter. We'll talk more about the issues with that. So that's what James Webb looks like now. Next slide. And we hope that with its capability in infrared, we can see all the way back to when the very first stars were born, when the dark ages ended. And that's why we used to call it fondly the first light machine. And we're pretty sure that now that the mirror has been tested and everything, that it is going to meet all the requirements that it's been asked to. So we hope that you'll be able to actually see the very first light that came into the universe. So what are the scientific goals for James Webb? Detect the end of the dark age. Look at the assemblies of galaxies as the galaxies evolved from the early universe to now. Scientists believe that the galaxies were much smaller then, and they became bigger because they started to merge together and collide together to get bigger and bigger. And actually that merger is actually happening all the time. Our own Andromeda galaxy, that's our neighbor, is coming very fast towards us, and one day they will merge together to create even a more beautiful night life. Hopefully humans are still there to enjoy it. And then look at the protostars, through the dust, to the nebula, inside the nebulas, how the new stars are born, how the planetary systems evolve around the stars, and how those debris field around the stars turn into a planetary system like ours. So next two videos will go over that. Next slide.
places where stars and planets are born are among the galaxy's most beautiful locales. These cosmic landscapes change as new generations of stars light up and disperse their birth cloud. But the youngest stars seen here are already perhaps 1,000,000 years old, hardly toddlers.
Stars and planets form in the dark, inside vast cold clouds of gas and dust, such as these pillars imaged by the Hubble Space Telescope.
The dust is so thick we can't see the infant stars inside, at least not with visible light.
With infrared light, Hubble can see through all but the thickest dust. Yet it's in those dense knots that the youngest stars are forming.
To peer inside them, astronomers need the James Webb Space Telescope.
With a mirror larger than Hubble's and performance optimized for the infrared, Webb will give astronomers their closest look yet at stellar birth.
We're flying through a computer model that represents astronomers' best ideas about the star formation process.
Reddish colors indicate thicker dust. The temperature, less than 400 degrees below 0 Fahrenheit.
Or less than 240 degrees below 0 Celsius.
That pinwheel ahead is a protostar, perhaps 10,000 years old. Protostars arise when a dense knot of dust, less than a light year across, collapses. But the details of the process are not well known.
Elsewhere in the cloud, another protostar is preparing to build planets. As the cloud that created the protostar collapsed, it flattened into a disk. The disk we see here is 600 times the size of Earth's orbit around the Sun.
If placed in our solar system, it would extend far beyond the planets.
In this computer model, the disk continues to accumulate gas and dust from its surroundings for thousands of years. Eventually, the disk fragments, producing dense, white structures. These may become sites where giant planets form.
Later, during another phase of construction, smaller Earth-sized planets may take shape.
At least, that's what scientists think happens. It will take the Webb telescope's keen infrared eye to see what's really going on in the cold heart of stellar nurseries.
Planets begin as dense knots in a cloud of gas and dust, swirling around a young star. But how do they go from something like this to something like this? With the James Webb Space Telescope, astronomers will be able to study how planets come to be and how they change as they get older. After centuries of searching, astronomers are finding exoplanets just about everywhere. Ranging from giant planets with masses much greater than Jupiter's to worlds only a few times more massive than Earth. But where do the planets we know best fit into the menagerie of worlds astronomers are finding? How did our solar system come to be the way it is? Why is Earth a balmy, water-rich world? And are there others like it elsewhere in the galaxy? These are the kinds of questions astronomers will address with Webb. For planets that pass directly in front of their stars, Webb will search for chemical fingerprints, identifying atmospheric gases like water vapor, carbon dioxide, and methane that absorb specific wavelengths of the star's light. Webb will also study the dusty disks where new planets form to reveal how the chemical compositions of younger and older disks change with time, and identifying how these changes are reflected in the planets we find. Such studies will be revolutionary in their own right, and by applying Webb's capabilities closer to home, astronomers will better understand planetary systems.
Next. So to do all those things, these are the four instruments that are installed and built inside the James Webb. Three of them are optimized in the near infrared, and then one of them is optimized all the way to mid-infrared, anywhere from 0.8 to 28 microns. So with these instruments, hopefully it will really widen up the window that we can study the universe with. The near cam also has a coronagraph, what you call a coronagraph. So imagine you trying to take a picture of a planet that's revolving around another star. Stars are very, very far away. Planets are very close to the star. Star is probably 10 billion times brighter than the planet. So how do you take a picture of a planet so close to such a bright object? Just imagine a firefly flying next to a searchlight. If the searchlight is off, you can probably look at the firefly. But when the searchlight turns on, you can no longer observe the firefly. So a coronagraph, what it does, which right now we still haven't perfected the technologies, to very strategically block out the light from the star enough so that we can actually take a picture of the planet itself. So that's a coronagraph technology. It's kind of a trial basis to see how well it can work. So James Webb has one of those capabilities on it. So hopefully we can actually image. We have never imaged an actual planet. We only discovered thousands of them by just observing its effect on its surrounding. The near spec also is basically a spectrograph. Like the video said, how do we tell if there's a planet and what it is made of, or even if a star, what the star is made of? And there's a technique or tool called spectroscopy, which is you take the light that's coming from there and you spread it into the range of wavelengths that it consists of. So if an alien being, or even us, take a star of sunlight that's coming through our atmosphere and do a spectroscopy, meaning put a prism in front of it and have it spread out, break out its various wavelengths. In those wavelengths, you will see the signatures of all the elements that are in our atmosphere, because each element has a certain frequency of light that they would absorb, and so you won't see that intensity of light in that wavelength. You will see dips. So by understanding what each element does to the light, you can really tell what that object is made of. So even though we cannot see a planet, but if we are fortunate enough that there is a planet around a star, eventually it will go in front of the star. And again, if you're lucky enough that that passage of the star, a planet is right in sight of our satellites, we can take the spectra of that light, if that planet has atmosphere, and we can study what its atmosphere is made of. So we can tell, what the abundant elements are in there. We also understand by looking at our atmosphere, if there is life on Earth, what signatures does the life produce? There's water vapor, there's oxygen, there's methane, which is a very big indicator of biological activities. So we can look for those kind of elements in the other planets to see if there is any chance of biological activity in those planets. So a spectrograph is a very important instrument, but it takes a long time to look at an object and take its spectra because they're so far away. So near spec, we had yet another technology we had to develop using the micro electromechanic machines, very, very tiny machines that can create a tiny slit in front of about 100 objects that are in the focal plane of James Webb. And a slit, of course, creates the spectra. So James Webb can take spectra of 100 objects at the same time. So it really is very, very efficient, and it can do the science much, much faster than what Hubble could do. So these are some of the instruments that are out there on the James Webb. So let's now move into the engineering challenges. So I'll just talk about two challenges that were actually caused by the third limitation. the astronomer said, we need as big a mirror as possible. Size of Hubble is not enough. Hubble has a limited IR. So if you were to make an IR instrument, we need a much bigger telescope so that we can see much, much farther. It can collect more light, more faster. And of course, they needed, they wanted 10 meters and whatnot. We didn't have the technology or the funding. So we negotiated, 6.5 meters. But then it needed to be at cryogenic temperatures. And I'll talk about why that is. And that created, figured out how to cool cryogenic temperatures, meaning minus 260, minus 270, 60 or 30 degrees centigrade. So how do we cool this telescope to that? So that created big structures to shade it from heat sources. But the problem was the launch capability. Just the mirror itself is 6.5 meters, but the biggest rocket we had can only fit 5 meters of a diameter. So we had to build these huge things, break them up into like an origami, to fold them into smaller pieces so that it can fit into the rocket. So these three things kind of drove all the engineering challenges and the technology development that we had to go through. So let's talk about the primary mirror. Next slide. Next slide. Next slide. So this is a comparison between a Hubble mirror, which is 2.5 meters, versus what we needed to build for James Webb, 6.5 meters. James Webb, the most perfect mirror we've ever built. The Hubble mirror is the most perfect mirror we had ever built. If we had Hubble sitting in Washington, D.C., and there was a firefly in Australia, it could take a picture of that firefly. But then it's a monolith. It's a single piece of glass of 2.5 meters, very finely ground and very, very thick, so that it could sustain the launch environment and does not get warped by the temperature changes in space and whatnot. It's very, very heavy. So of course we knew how to build this one, so why not build same technology mirror, 6.5 meters. Two issues: we couldn't fold it to fit in the rocket, and secondly, it'd be so heavy that that rocket won't be able to lift it. So we had to think about how can we make the 6.5 meter mirror that is light enough, strong enough, and foldable enough. So we went to what we call the segmented mirror approach. So just think about it. We build a 6.5 meter perfect mirror. You chop it up. You put each of those chopped up pieces on a frame that can fold, so that you can actually fit it into the rocket. So it's kind of that, but what we did was we built 18 single mirrors that can be installed rather than building one and cutting it up, which didn't make any sense. So we built 18 mirrors. Each and every one has a certain portion of the total prescription of James Webb. And so we will place it so that once it's folded back up, it will act like a single mirror. So segmented mirror technology and what material to use and how to make it very, very thin and lightweight and yet strong took a lot of years and a lot of money to figure that out. So now the 6.5 meter mirror altogether, including the frame and everything, is no heavier than the Hubble mirror. Next slide. And this is what it looks like. The total fully deployed mirror. You can see how big it is compared to the humans in the clean room. Next slide. Next slide. No, I'm sorry, go back. Then we had to figure out we need to test these things. We cannot just build them and throw them up in space. We got to make sure it's going to work, because there's no way to go and fix anything. So we needed big enough chambers that will take this mirror. So fortunately we had an Apollo program, that had ended in the late 70s. It had huge chambers, but they were used for different reasons. So we had to modify all of those chambers to our needs. And this is the mirror inside one of those chambers is being tested for thermal environments and also for prescription. Next slide. This is a portion of it, and this is how it looks like when the frame's folded up. And so it's in 3 segments, the central segment and 2 wings. So when you do that folding, it can fit into the rocket. Next slide. But how do you know that we have 18 different mirrors? We have put them together. It's going to shake up during launch. It's going to unfold, and there's no reason to believe that they will remain in the position that we first installed them. So how do we have the capability to make sure that we can align those mirrors if they are unaligned? So that was yet another technology we had to develop called the wavefront sensing and control. And next video we'll talk about how that works. But basically, you think of when the mirrors are folded up, you basically have 18 different mirrors. If you take a picture of a star with 18 mirrors, each mirror will put the focus of that star some point outside of the focal point, because they are out of alignment. So we had to do reverse engineering to say, okay, take this image, it's so far to the right or the left of the focal center. So how do we move this mirror up, down, left, and right to bring that image to the center? And in the next slide. So to do that, we have actuators at the back of each of those 18 segments. And the step is very, very small. It's 1/10,000th of the size of a human hair. Each step can move the mirror by that slight amount, left, right, up, or down. And there's some actuators in the middle, so if the shape of the prescription has changed, we can actually pull or push in the middle of the single mirror to change its shape. So the next slide shows how we do that. Next slide. There's no audio there, so we just have to read. So again, each and every mirror is a hello. So each and every mirror actually has to go through 18 different steps to be formed, anywhere from digging for the material, beryllium material, which we finally figured out what material to use. The next video quickly shows you what all the steps each and every signal mirror had to go through before it could be launched.
Our most powerful window of the universe is nearing final assembly. A 21-foot diameter segmented array of mirrors is the heart of NASA's James Webb Space Telescope. This powerful successor to the Hubble Space Telescope will allow humans to see farther into the universe than ever before. This Herculean effort has pulled together technical experts from across the nation. The Mirror Odyssey begins in a mine where the precious metal beryllium is extracted. Beryllium is the choice for the air material, The telescope will then be rolled into the giant thermal vacuum chamber used to test the Apollo lunar spacecraft. After that, the two-story high optical telescope assembly will be attached to a 10-sport-sized sunshade designed to deflect heat from the sun. The telescope's gold mirrors will be used to seek our cosmic origins by seeing the earliest galaxies and perhaps detect the first glimmer of life on an alien world.
Next slide. Okay, the next challenge was temperature control. So, like I said, the telescope needed to be at cryogenic temperatures. Why is that? It's an infrared telescope, right? So everything that it's looking at is coming from a distance, it's in infrared light. But infrared light is emitted by anything that has temperature. I'm emitting infrared light, you guys are emitting infrared light. And if the telescope is warm, let's say it's launched at room temperature, when it's in space, it's going to get heat from the sun and all that. It's going to have a certain temperature, and it's going to emit infrared light as well. And so how do you know that the image you're looking at is the telescope's light or the image that's coming from the universe? So to reduce the confusion, you need to figure out how to eliminate the infrared signal that's coming out of the telescope, and therefore you cool it. You cool it so low that the signal to noise ratio is large enough that you can now actually image the thing without getting polluted by the temperature of the telescope. But how do you cool these huge things to these low temperatures? Of course, we could put refrigerators and cryo coolers and whatnot to cool various parts of it, but that it adds complexity, that adds weight, and all those issues. The other easier approach is to make use of what we have in the universe. And we know that the universe, this space, is the perfect heat sink. It's at almost 0 degree Kelvin, 4 degree Kelvin. And so we can reject heat from the telescope into space and let it cool down passively. You can do that, but then of course there is sunlight hitting it, so it's going to heat it up again. So the only way to get to that temperature is to figure out how much sunlight you got to block from hitting the telescope, or even the Earth's reflection or the moon reflection hitting the telescope, and let it radiate so that when the equilibrium occurs, it's at that temperature. So, next slide. The solution is actually very simple. You put a sun shield between the telescope and the sun, or the source of heat. And we decided, okay, we need 5 different layers, and I'll talk about how they work. Create a sun shield. And next slide. So we have 5 layers. This is how this works. The sun is coming from here. The telescope is on this side. Sunlight is about 1400 watts per square meter flux at that orbit. And so it hits the first shield. Most of it is reflected because of the coating on the shield. But of course the shield gets hot, so it starts generating infrared light, which gets bounced off by the next layer out to space, and so on and so on. So by the time the last shield is there, it only allows out of 1400 watts per square meter to maybe microwatts. And so only microwatts of energy from the sun is hitting the telescope, and it's radiating its own the power that's creating the electronics and whatnot, or heating of the telescope. They get radiated into space. So the concept is very simple. The issue is the size. To protect the whole telescope and allow it to look left and right while still protecting from the sun behind, it needed to be a certain size, and the size turned out to be almost the size of 1 tennis court, and then 5 of them. And of course those don't fit into a 5-meter fairing of a rocket. So the technology challenge was how to roll these things. These are very, very thin materials. I don't know if you ever tried to pull out a saran wrap or something to cover your food. It always gets screwed up, so it never comes out smooth. So how do you make sure that these things can be rolled in when we launch, and after launch it comes out smoothly without getting stuck and so forth. So that's where the challenges was. So in the next video shows you how many humans and how many hours it took to test the rolling in and out of the sun shield. And so the next slide. You don't have to have the sound, I think don't worry about the sound. So it's a very methodically, this is of course in fast forward, so it's going fast, so it takes hundreds of hours to actually pull it out to make sure everything is going smoothly. And then pull it out and then separate them in 5 layers. So you get the idea. So all of that has to happen once it's rolled in, things is launched, all of that has to happen automatically with the machines and mechanics. No human intervention can be sent there to pull this sun shield out. So that's where the biggest technology challenge was to figure out how to protect the telescope with this sun shield that has to be rolled up to fit into the rocket. Next slide. So this is why we call it origami. So the telescope, when it's fully deployed, looks like this, and when it's in the rocket, it looks like that on the right. Next couple of slides kind of show you a little bit more. Next slide. That's in the rocket, how it's sitting in the rocket. Next slide. So the next question is, where do you send this telescope? That's the most optimum orbit for it. Of course, Hubble is in the low Earth orbit. It's only 500 kilometers above the Earth, and it's going around the Earth at 18,000 miles per hour. But of course, it's getting the heat from the sun, it's getting the heat from the Earth and the Moon and so forth. So we have different requirements for Hubble, so it's okay to do that. But James Webb couldn't do that because the sun shield would have to be so complicated and articulating to track the sun. So we know that there are few orbit points discovered by Lagrange, that any two massive bodies create 5 Lagrange points where you can, in the simple terms, think of it that the gravitational forces of the two bodies almost become equal to each other, and so there's a very stable point. There's no gravity wells anywhere near that point. So if you can orbit something under Lagrange point, it will stay there with very little fuel required to maintain the orbit. So we decided to send James Webb into Lagrange point number 2, which is 1.5 million kilometers away from the Earth. And the next video will show you how that works. It's basically the Lagrange point moves with the Earth, and of course the telescope is always facing away from the sun, and as the Earth goes around the sun, so does the telescope, and so it has view eventually to the 360 degrees of the universe. So over the course of 1 year, it can observe the entire universe to a certain limitations of moving left and right or up and down, so that it can observe the sun. So I'm very happy to announce that James Webb has actually reached that point. All the things have been deployed, mirror has been checked out, it's all working beautifully, and so I think pretty soon it'll start doing the science that we hope it will do. Next slide. Of course, Hubble is still out there. It's been there for 32 years, and we hope it will continue to work. But nothing right now is wrong with it. All the systems are working. Some of them are, of course, on their redundant side, but it's still working fine. So together with visible observatory and a far mid-infrared observatory, I think we have opened up the window to the universe to a new eyesight, and we can't wait to see what it discovers, what questions it answers, and we're also sure that we'll also find some new mysteries that we don't know the answers to, and we're going to count on you kids here to answer those questions when you grow up. So that's all my presentation. I appreciate your attention. Thank you very much.